For our work in Chapter 6, so far, we've just been looking at enthalpy in terms of what is delta H and what is it for different reactions. For this last section of our book, we're going to be looking at how to actually calculate those delta H values. And we're going to do it through two different ways. Okay. This first way, on this first half of the paper, we'll be looking at our enthalpy of formation. The second way will be using Hess's law. Okay, and they both kind of work under the same assumption or the same concept here, and that is that enthalpy is a state function. What that means for us is our delta H is going to be the enthalpy of our final minus the enthalpy of our initial. Or in other words, for a chemical reaction, our final is going to be the enthalpy of our products minus the enthalpy of our reactants. So enthalpy of formation. What we're going to do is we're going to say that our change in enthalpy is going to be a result of breaking down everything that we're looking at, all of the chemicals, into their lowest state, okay, their lowest energy state, so by themselves, getting them to their almost atomic form, and then putting them back together again. So that's our delta H of formation, or enthalpy of formation. So our enthalpy of formation is the change in enthalpy associated with the formation of 1 mole of a compound from its elements in their natural state. And we assume that when our elements are in their natural state, their lowest energy state, their enthalpy is 0. So any formation that we do, okay, our reactants component or our initial component would be 0. So if we can measure the enthalpy of that reaction, say from one of our calorimetry options, then the delta H is associated directly with the enthalpy of our products. So when we say this natural state, what we mean is our lowest energy state. So for metals, that will be there as an atom, so a single atom in the solid state. So let's say iron would be listed like that. Any of our diatomic molecules, they will have to be molecules. So we have O2 as an example, and it's in a gas state. Sometimes we can have two different types of solid states, and we want to take the lower of those energy. So for example, carbon has two solid states, either graphite or diamond. And graphite would be the lowest energy state for carbon. Another random one that you might show up in some of your examples, sulfur has some different crystalline arrangements, and S rhombic. And we'll talk more about crystallization in the next quarter. But for now, all you need to know is that S rhombic is the lowest energy state. So all of these here would have an enthalpy value, so an H value of 0 kilojoules per mole. Everything in the lowest energy state. All right. If you wanted to work with these in an example, okay, we can look up these delta H values in tables. So Appendix 3, as well as there are some listed in Table 6.4. So 2 places that you can look for delta H of formation values. And we work on the assumption we're going for our products minus our reactants. So we're going to look at the sum of our product enthalpies and the sum of our reactant enthalpies. So how much energy or how much heat it took to form our products and our reactants. And the difference of that will get us the delta H of formation of the entire reaction itself. So if we take a generic equation where the lowercase letters are the coefficients, the capital letters are the chemical components. Delta H of our reaction is going to equal the sum of our products minus the sum of our reactants. So we will have the coefficient, our lowercase c, times the delta H of formation of compound C. And so that's a capital C there. So we can kind of tell the difference. We're going to add that to the coefficient lowercase d times the delta H of formation of compound D. Okay, again, these values you would look up in Appendix 3 or potentially Table 6.4. So that's the sum of the change in enthalpies for our products. Now we want to subtract the sum of our enthalpies of our reactants. So we would have our coefficient of A times the delta H of formation of compound A plus our coefficient for B times the change in enthalpy of formation of compound B. Now, these values, these enthalpy values can vary for different temperatures, different pressures, and so we have a standard state that we like to work with, and when we are at standard state, everything has this knot here, that's what it's called, it's just a little circle, and what that circle indicates to us is that we are at standard state conditions. Which is actually different than the standard state conditions of gases in that our temperature is 25 degrees Celsius or room temperature. Okay, so STP corresponding to gases, temperature there is 0 degrees Celsius. For our standard state conditions in terms of thermodynamics, we take our temperature to be 25 degrees Celsius. Pressure, if we're working with gases, would still be 1 atmosphere. This equation here, you don't necessarily have to know and be able to reproduce this exact equation, but you need to be able to apply this equation to doing a calculation, which we will do in this example here. Okay, so you need to know it, not regenerating it, but using this concept, using this reaction. So let's work an example. We have what is delta H of the reaction for the combination of nitrogen and oxygen gas forming dinitrogen tetroxide gas, so N2O4. So we're just following this setup here. We have our products minus our reactants. So delta H of our reaction is going to be 1 times the delta H of formation of N2O4 minus 1 times the delta H of formation of N2 and 2 times the delta H of formation of O2. So we look these up in a table on an exam. They would be given to us. From the appendix, we'll see that the heat of formation of N2O4 is equal to 9.66 kilojoules per mole. Nitrogen, as N2, is in its lowest state, so it has an enthalpy of 0 kilojoules per mole. Same thing for oxygen. It's in its gas phase and a molecule, so it's in its lowest energy phase. So by definition, the heat of formation of it is also 0. These values would not be given to you on an exam. You need to know and understand that the heat of formation of items or chemicals in their lowest energy state are going to be 0. So our delta H of our reaction, easy calculation, we're going to have a positive 9.66 kilojoules per mole. No, the positive, putting that plus there is not required. I try and get in the habit of when things are positive, I put the plus in, just so in case I look at it, I don't have to question myself, well, was that really negative or not? If I put the plus in, I know that I intentionally made that positive. In the next video, we'll go through Hess's law, okay, an application of that, where we again deal with enthalpy as a state function, but instead of looking at things being formed from their lowest energy state, we're going to take the reaction through a series of steps that eventually will get us to our products.